Hello everyone. So today we will be going through qualitative analysis. So there are chemical tests to identify cations, anions, as well as gases. So this whole chapter just revolves around the 4 different tables, which are the 4 different tests. Okay, so let's start with cations first. So for cation, we can use sodium hydroxide solution, NaOH, or aqueous ammonia to identify the cations. So what can we do? To a solution containing a positive ion, we can add aqueous sodium hydroxide or aqueous ammonia to see what is the change. Okay, so there's 2 stages for adding the sodium hydroxide or ammonia. The first one is to add a few drops, then later add in excess, and then write down what you see. What are your observations? So to confirm the identity of a positive ion, after adding sodium hydroxide or ammonia, look for the color of the precipitation, as well as if the precipitation dissolves in excess sodium hydroxide or ammonia. So let's take a look at first test, testing of cations with sodium hydroxide solution. Okay, so again, this is the case when we add aqueous sodium hydroxide to a solution containing an unknown positive ion. So we can divide this into 3 parts. It'll be easier to start from the ones that are colored first. So Fe2+, if Fe2+ is present, you will have a green precipitate of iron 2 hydroxide formed. Now, why would you have hydroxide? You will have Fe2+ because Fe2+ is present, correct? And then you added sodium hydroxide. So sodium hydroxide is the source of the hydroxide ions. Hence, they will add up to form iron 2 hydroxide, which is a green precipitate. And then in excess NaOH, the green precipitate remained. Okay, next, Fe3+. So if Fe3+ is present, after adding a few drops of NaOH, you will see a reddish-brown precipitate of iron 3 hydroxide formed. Iron 3+ because it is present, plus 3 OH- ions, which comes from the sodium hydroxide solution. So together they will add up to give you iron 3 hydroxide, which is reddish-brown. So upon adding excess NaOH, your reddish-brown precipitate will remain. Okay, so meaning it will still remain as it is, as a reddish-brown precipitate. Next, Cu2+. If Cu2+ is present, you will have a blue precipitate of CuOH2 formed. So here is the ionic equation, and upon adding excess NaOH, you will have blue precipitate remaining. So these 3 are the colored precipitates. After you do a few questions, you will realize that these 3 colored precipitates would be the easiest for you to remember. Next, let us take a look at the non-colored ones. So calcium, Ca2+, Zn2+, Al3+, and Pb2+. These 4 will all form white precipitates upon addition of a few drops of sodium hydroxide. So for calcium, so if calcium is present, you will have calcium hydroxide formed. If Zn2+ is present, you will have zinc hydroxide formed. If you have Al3+, you will have aluminium hydroxide formed. And lastly, if Pb2+ is present, you will have PbOH2 formed. So over here, it is the same logic because you have those cations present. In addition to the hydroxide ions from the sodium hydroxide solution, it will form a hydroxide. Okay, so those white precipitates are the different hydroxides that's formed. Then next, when you have excess NaOH, what will happen? So over here, it will be very interesting to note that the white precipitate dissolves for Z. Remember what's that? That rings a bell, right? Z refers to the amphoteric oxides. They are amphoteric, meaning that they will react with both acids and bases. Okay, so let us see. What will happen when the white precipitate dissolves? So for zinc hydroxide, the equation is ZnOH2 plus NaOH. And it will give you a complex ion known as sodium zincate. Na2 ZnOH4. Yep. So then how did we even come to have this sodium zincate? So let's take a look at the charges. Zn has a +2 charge. OH has a -1 charge. Over here, there are 4 OH, so therefore overall it has a -4 charge. So overall, it will have a -2 charge. So then, what will happen is, it will look like that. It will be ZnOH4, 2 minus, and then Na will be Na plus. So if you swap them, you will get Na2 ZnOH4. Okay, so that's how you come to derive the formula of sodium zincate. Next, you have to balance the equation. So there's 2 Na on the right, so therefore you add 2 to the front of NaOH, so that you also have 2 Na on the left. And then let's take a look at all the other elements. You have a total of 2 plus 2, 4 oxygen on the left. You also have 4 oxygen on the right. Let's look at hydrogen now. You have, again, 4 on the left, as well as 4 on the right. You have 1 zinc on the left, 1 zinc on the right, and 2 Na on both sides. Okay, done. This is balanced. Okay, next. What about aluminium hydroxide? So since aluminium hydroxide is also amphoteric, therefore it is able to react with sodium hydroxide, which is a base, to form a complex ion. So AlOH3 plus NaOH gives NaAlOH4. So this is known as sodium aluminate. So again, let's see how we derive this formula. We have Na plus, we also have AlOH4 minus. How do we get AlOH4 minus? Because Al has a charge of +3 and OH has an overall charge of -4, since there's 4 of OH minus. So therefore overall it has a -1 charge. So that's how we know it's AlOH4 minus. And then when you swap these two together, you will get NaAlOH4. Okay, so that's sodium aluminate. Over here, it is balanced. Lastly, for lead hydroxide. Now, lead hydroxide is the last amphoteric oxide. So hence, you form PbOH2 plus NaOH, and it will give you NaPbOH4. So this is known as sodium plumate. Is it balanced? Let's see. Sorry, I think there is Na2 PbOH4. Why is this so? Because Pb is +2, and OH is OH minus, as 4 of it, so -4. So over here, you will have overall charge of -2. So it will give you PbOH4, 2 minus. And then with Na plus, it will give you this compound sodium plumate. So to balance it, we need to add a 2. So we are adding a 2 in front of the sodium hydroxide. Okay, so these are the equations. So these are the equations to help you to see why the white precipitate will dissolve. They dissolve because the new compound, the new product, is no longer insoluble in water. It becomes soluble in water. So that's why white precipitate will dissolve. Okay. So for calcium 2 plus ions, the white precipitate remained. Okay. And then the last one, for NH4 plus, there is no precipitate form. You only have ammonia gas released when heated. Okay. So if you would like to know why, I can give you an example. For example, ammonium chloride. If I react it with sodium hydroxide, it will react to form NH3 plus H2O, NaCl. Okay, so this is why, although there's no precipitate form, you will have the ammonia gas released when heated. Okay, so over here for the first table, I would say that in general, it's still rather easy to remember. Okay, so you remember them by the colors, which are those with colors, and then you remember the NH4 plus does not have any precipitate. Then the rest would be white color. So for this is for a few drops of sodium hydroxide. For in excess of sodium hydroxide, what you will have to do for this, you need to remember that all the colored precipitates will remain undissolved, okay, in excess NaOH. Whereas, so you will have the precipitate remaining in excess NaOH for everything except for Z. So this would be a very easy way for you to remember it. So over here, I would like to ask, how come all of these are precipitates? Why are all of them precipitates? So you can pause the video to give yourself some time to think over this question. Okay, so I think most of you should have guessed it. It's because if you remember from the solubility table, all oxides and hydroxides are insoluble except for group 1 and strontium and barium oxides and hydroxides. So hence, if you notice, all of the cations here do not fall under group 1, nor strontium and barium. So therefore, they are all insoluble in water. So that's why they all form precipitates. So next we'll be testing for cations with aqueous ammonia instead of sodium hydroxides. So over here, let's go to the colored compounds first. So green precipitate of FeOH2, iron 2 hydroxide formed again. So some people might ask, how come we form a hydroxide again? How come it's the same as sodium hydroxide? Because in this case, I added aqueous ammonia. There's no hydroxide inside the name. So how come I will get a compound containing hydroxide? It is because aqueous ammonia is a weak base. So when dissolved in water, it will give ammonium hydroxide. Of course, this is a reversible equation because it's a weak base, so only a small amount of NH3 would become NH4OH. So therefore, there's only a small concentration of OH minus ions. But nonetheless, it still gives us ammonium hydroxide, right? So the hydroxide in ammonium hydroxide is what is responsible for the hydroxide in the compound. So hence over here, the ionic equation is exactly the same as the sodium hydroxide one. And when we add excess aqueous ammonia, the green precipitate remains. So this is the same as the previous aqueous sodium hydroxide. Next, Fe3+. When Fe3+ is present, we will have a reddish brown precipitate of iron 3 hydroxide formed. So same ionic equation and same observations after adding excess aqueous ammonia, the reddish brown precipitate remained. And the last colored compound is copper 2 plus. It will give you a blue precipitate of copper 2 hydroxide. Okay, this is the ionic equation. So the difference is that the blue precipitate will dissolve in excess aqueous ammonia to give a dark blue solution. So this is where it's different from the sodium hydroxide observation. So please take note of this. The rest are the same. Next, for the white colored precipitate, there's some changes, okay? Firstly, take note that Ca2 plus will have no precipitation when you add a few drops of aqueous ammonia. So this is something to take note of. So why is there no precipitation for calcium 2 plus ions? It's strange, right? Because just now with sodium hydroxide, there is a white precipitate formed. It's because in this case, we are adding ammonia, which like we just said, is a weak alkaline. So being a weak alkaline, it means that it partially ionizes in aqueous solution to form a very low concentration of hydroxide ions. So since the concentration of the hydroxide ions is low, calcium hydroxide remains soluble. Hence, no precipitate formed. So let me write that down. So ammonia is weak alkaline, low concentration of OH minus ions. Therefore, CaOH2 remains soluble. So no precipitate is formed. Even when we add in excess ammonia, there is still no precipitate formed because, like we mentioned, your OH minus, you have a very low concentration. So it's not strong enough, you don't have enough to displace out the original N ion that is bonded to Ca2 plus. Therefore, there is nothing, no precipitation for calcium ion. Next, for ZAP. So ZAP, they are still white precipitates like before. So white precipitate of zinc hydroxide, same ionic equation, similar to the one above, white precipitate dissolves. So the equation for the dissolution will be the same equation. It will form sodium zincate. So I'm not going to repeat the equation, but I will just write down the product here. Next, for aluminium 3 plus, you will have a white precipitate of AlOH3 formed. This is the ionic equation. But over here, take note that the white precipitate remained. Again, the reasoning is because you only have a very low concentration of hydroxide ions. So for aluminium and lead, it is not sufficient to form the sodium aluminate and sodium plumate respectively. Okay, for lead 2 plus, it's the same. You have a white precipitate of PbOH2, same ionic equation. Okay, so I hope that this helps you to remember the two different tables. So please take note that it's very important for in QA for you to know these two tables. If you don't know these two tables, you wouldn't be able to do any of the questions. So next, let us take a look at the tests for negative ions, for N ions. So to confirm the identity of a negative ion after adding the reagents, note the following observations. So for nitrate and carbonate, you test for the gas that's released. For chloride iodide, SO4 2-, as well as bromide. You observe the color of the precipitation. So here is our table. So nitrate would be the one that is the most complicated. To test for the presence of nitrate ion, add aqueous NaOH followed by aluminum foil or aluminum powder, then warm it carefully. So what will happen? Let's take a look. So nitrate ion, once you add in sodium hydroxide, you will have a hydroxide instead. Okay, let us write it down in terms of the equation. Let us assume that we have sodium bonded to the nitrate. So sodium nitrate plus NaOH. So you will get sodium hydroxide and then plus aluminium foil or powder. What will happen? The aluminium will reduce it. Okay. So in the presence of water, what you will get will be sodium aluminate. And with the reduction by Al, next, let's look at carbonate. For carbonate, you can add any acid and use lime water to test for the gas release. Why is that so? Because if you recall, acid plus any metal carbonate will give you salt plus carbon dioxide plus water. Correct? So therefore, since you have carbon dioxide produced, you can use lime water to test for the presence of this carbon dioxide. So therefore, if carbonate is present, it will produce carbon dioxide and you will observe effervescence, and the white precipitate formed in lime water when CO2 produced is bubbled into it. Next, chloride, bromide, and iodide. These three are linked because all three of them are halides. So what do? Firstly, you add dilute nitric acid. So a lot of people might ask, why do I add dilute nitric acid? This is to remove any carbonate present, as silver carbonate will also give a white precipitate which will be rather misleading. Okay, so for the steps, you will have to add dilute nitric acid followed by aqueous silver nitrate solution. If chloride is present, you'll have a white precipitate of silver chloride, which is formed. So the Ag plus comes from the silver nitrate, Cl minus comes from the chloride that is present. Together, they will combine to form silver chloride, which is a white precipitate. So let us take a look at the steps. Why do we add dilute nitric acid? It's because if we add dilute nitric acid, it is to remove any carbonate present in the solution, as silver carbonate will also form a white PPT. Then you have positive results for Cl minus when Cl minus is not present because it is carbonate that is present instead, right? So we don't want to have this kind of false positive. So that's why we first add in a dilute nitric acid so that the acid can react with the carbonate and release CO2. Okay, so that after that, when we add in aqueous silver nitrate, any white precipitate that is formed is only due to the presence of Cl minus. So over here, there is another solution that you can use. You can also use lead 2 nitrate solution instead of silver nitrate. Why is this so? If you recall, this is based on your solubility table because all chlorides are soluble except lead and silver chloride. So therefore, that's why as long as you put in lead 2 nitrate or silver nitrate, it will form lead 2 chloride and silver chloride, which will both be a white precipitate. Understand? So for bromide, you also do the same thing. Exactly the same reagent used. It's just that the product is different. You will have a cream precipitate of AgBr4. Okay? So it is cream, so the ionic equation is Ag plus Br minus gives AgBr. Next, it will be I minus. So iodide, also the same thing, add dilute nitric acid, followed by aqueous lead 2 nitrate solution or silver nitrate solution is also okay. you will get a yellow precipitate of PbI2 formed. And here is the equation. So you notice that for the halides, you will get different colored precipitates, white, cream, and yellow respectively for chloride, bromide, and iodide. And lastly, the last anion is sulfate. So for sulfate, again, you have to add dilute nitric acid, again, to remove any carbonate that might be present, because most carbonates are insoluble. So therefore, most carbonates will form a white precipitate, which will give you a false positive. So after that, add in aqueous barium nitrate solution, you'll get a white precipitate of barium sulfate form. Please take note that between your Pb2 plus and your Al3 plus, you realize that both will give you the exact same observations when you add both aqueous ammonia and aqueous sodium hydroxide. So how do you differentiate between them? We have to use iodide ions to distinguish them. So it's because for Pb2 plus, in the presence of iodide, it will give you lead-2 iodide, which is a yellow precipitate. Whereas for aluminium Al3 plus iodide, it will give you aluminium iodide, which is a white solution, because it is soluble, so therefore it will be soluble, so it will be a solution. So this is different from the precipitate. So this is how we distinguish between Al3 plus and Pb2 plus. Okay, next, please take note that lime water, which has the formula calcium hydroxide, CaOH2, it can react with carbon dioxide to form a white precipitate of calcium carbonate. This is the reaction. So this is why you will have a white precipitate formed in the presence of CO2 and lime water. In excess carbon dioxide, calcium carbonate redissolves to form soluble calcium bicarbonate. So this is why you'll notice that when you're using lime water to test for carbon dioxide, after a while, your white precipitate might suddenly disappear. Okay, and you'll form a colorless solution. So this is because when in the situations where you have excess CO2, the calcium carbonate redissolves to form something soluble. So that's why you will see the white precipitate being soluble. But it doesn't matter, because as long as you have seen the white precipitate before, it means that carbon dioxide is present. It is being produced. Okay, next part. Last part, let's take a look at the tests for gases. So this is quite simple for most of you. Okay, so it's just like a revision. So how do we test for ammonia? We use damp litmus paper. It will turn the damp litmus paper blue because it is basic. Correct? For carbon dioxide, we use lime water, like I just said. We will have the formation of a white precipitate which dissolves in excess CO2. For chlorine, we can use damp litmus paper. So over here, it's recommended that you use a damp blue litmus paper. The result is that the damp blue litmus paper turns red and then is bleached. So there's two steps. The blue litmus paper turns red first and then is bleached. Okay. For hydrogen, we use a lighted splint. The lighted splint will extinguish with a pop sound. For oxygen, use a glowing splint because oxygen supports combustion, so the glowing splint relights. And lastly, for sulfur dioxide, SO2, this is a reducing agent. So you can test for the reducing agent using an oxidizing agent. In this case, you have acidified potassium dichromate, K2Cr2O7, which is an oxidizing agent. So your K2Cr2O7 will be reduced, and so the color change will change from orange to green. So this last table would be the easiest because you have done most of it. Okay, great. So very quickly we finished this entire chapter. So now we are going to try out some questions. So the questions that we will be trying out here during the lesson is, so please try the following questions 2, 3, and 4, and please pause the video now. Okay, go ahead and do the questions, attempt them, and once you are done, continue the video again. Okay, so for question number 2, a carbonate compound X produces black oxide M and gas N upon strong heating. Gas N causes a white precipitate form in lime water. Okay, so from this sentence, it's very obvious that NO2 will be carbon dioxide. So let me write that down. So notice that in the question they said identify. Identify means that you can either name it or you can write the formula. So either will be fine. And then next, substance M is subsequently added to dilute sulfuric acid. So the solution becomes clear blue solution and is divided into two portions. For the first portion, blue precipitate P is formed when NaOH is added to it. So this sentence also tells us that we have Cu2 plus present. So over here, they added M to dilute sulfuric acid. So that means P must be copper 2 sulfate. CuSO4. For the second portion, acidified barium nitrate solution is added. White precipitate Q is formed. So this one is also rather obvious that this tests for the presence of sulfate. So hence, for Q, we have barium sulfate because we added barium nitrate to something containing sulfate. So therefore, we will have barium sulfate. So you can either spell out barium sulfate or BaSO4. And then next, as for M, let's take a look. M is subsequently added to sulfate, so sulfuric acid. So the sulfate doesn't come from the M, but it comes from the dilute sulfuric acid. So let us go in front and take a look. So a carbonate compound X produces black oxide M. So I think we have our answer that M is copper 2 oxide then. And X is a carbonate. So therefore it will be copper 2 carbonate. So you can also write it as CuO or CuCO3. A solution Y undergoes a series of chemical tests, and the results are shown below. Number 1, effervescence is observed when calcium carbonate is added. So what does this tell us? This tells us that, well, you have a gas produced because we have effervescence. So if you have a carbonate, then most likely it means that an acid is present because acid plus carbonate will give you carbon dioxide, which will be responsible for the effervescence. Next, number 2, no precipitate is formed when either acidified silver nitrate solution or acidified barium nitrate solution is added. So over here, it means no Cl minus. And when there is no precipitate form when you add acidified barium nitrate, that means no sulfate either. Number 3, when the solution Y is warmed with NaOH and aluminium powder, a pungent gas is released which turns moist litmus paper blue. So because it's pungent plus it turns litmus paper blue, it tells us that ammonia is present. Okay, and because ammonia is produced when Y is warmed with NaOH and aluminium, it tells us that Y contains nitrate ion, NO3 minus. So they asked us to identify solution Y. Well, from observation number 1 and 3, if I piece them together, I know there's an acid, and I know it contains nitrate ion. So that only gives us one answer, nitric acid. Agree? Yep, and that's it for question 3. And lastly, for question 4, the diagram shows a reaction scheme. Name substances A to E. So note over here that they ask us to name it. So we have to give the name, we cannot give the formula. Let's see what happens. So solution A, when I add aqueous ammonia, I will have a brown precipitate B. So brown precipitate, what does this tell us? There's one thing that rings a bell in the aqueous ammonia chart. The only thing that's more similar to brown would be reddish brown. And that would be when you have Fe3 plus present. Okay, let us confirm whether this is correct, because over here they didn't say reddish brown, they said only brown. So let's see, after we add in dilute H2SO4, we will have a brown solution C. So if it is Fe3 plus, it means that over here, the brown precipitate B will be iron 3 hydroxide. And then after adding sulfuric acid, it will be iron 3 sulfate. And then when you add SO2, which is a reducing agent, you get a green solution. Now, green solution, I know it contains Fe2 plus, right? And does it make sense? Well, over here we have Fe3 plus. The oxidation state decreases from +3 to +2, so therefore it is being reduced. So that would be the function of the reducing agent, to reduce Fe3 plus to Fe2 plus. So it all fits. So therefore my guess was true. So therefore let me write it down. So my brown precipitate B will be iron 3 hydroxide. My brown solution C will be iron 3 sulfate. And then green solution D will be iron 2 sulfate. Because the sulfur dioxide added is only responsible for reducing Fe3 plus to 2 plus. The anion doesn't change. Okay, now let's take a look on the other side. When I add acidified silver nitrate to solution A, I will get a white precipitate E. So over here, this indicates the presence of Cl minus. So hence white precipitate E will be silver chloride. And in A, this means that it contains both iron 3 and chloride. So together, that will be iron 3 chloride. So that's how we get all the substances A to E. Next part B, write the chemical equations for the formation of brown solution C from brown precipitate B. So brown precipitate B is FeOH3 plus dilute H2SO4 give you Fe2SO43. Okay, what else? So FeOH3, this is a hydroxide, so it's a base, plus H2SO4 is an acid, so it's neutralization. Therefore, I will also have H2O. So now I just need to balance this. I have 2 Fe on the right, so I need times 2 on the left. And then I have 3 SO4 on the right, so I need to times 3 on the left. So let's see. Then next on the left, I have 3 times 2, 6 plus 6, 12 hydrogen. So to balance it on the right, I times 6 in front. Let's check the oxygen. I have 3 times 2, 6, 6 plus 4 times 3, 12, meaning a total of 18 oxygen. On the right, I have 4 times 3, 12, plus 6, 18 oxygen as well on the right. So hence, this is all balanced. So this would be okay. So if they don't ask for state symbols, do not write it, because if you make any mistake with a state symbol, you will be penalized for it. But if you need to write it, FeOH3, it is a precipitate, so hence it's a solid. Next, H2SO4 is an aqueous. Fe2SO43, they said that it's a brown solution, so hence it is aqueous, and 6H2O is liquid state. Next, write the ionic equation for the formation of white precipitate E from solution A. So over here, for part C, it would be Ag plus from E plus Cl minus from A, and together they'll form AgCl. Okay, so if you need to write state symbol, here are the state symbols. Part D suggests another substance that could replace acidified silver nitrate solution to form white precipitate E. Just now we've talked about this when we were going through. Another thing that can replace acidified silver nitrate to form silver chloride will be lead to nitrate. So lead to nitrate. And lastly, describe how green solution D is formed from brown solution C. So over here, iron 3 sulfate is an oxidizing agent, and sulfur dioxide is a reducing agent. Hence, sulfur dioxide causes Fe3 plus ions to reduce to Fe2 plus. The presence of iron 3 ions gives the solution a green color. Okay, so this is how D is formed from C. Okay, that's it. So for homework, I would suggest you do all the multiple choice questions over here in this table, especially do question 2, do question 3, and question 1 and 2. Okay? Okay, that's all for today. Thank you so much, and see you again soon. Bye-bye.